Hello students, in this video we'll prove the open mapping theorem for non-constant holomorphic functions on a domain. Let's be given f mapping omega into C, a non-constant holomorphic function on a domain omega. Then f maps an open subset of C into an open subset of C. Then f maps open sets onto open sets. Hence, f is what's known as an open mapping. And this theorem is therefore called the open mapping theorem. So this is the open mapping theorem. Okay. All right, excellent. Of course, recall a subset E of C is open if for every W in E, there exists an R greater than 0 such that what? Such that the disk centered at W of radius R is contained in E. Contains a small disk about that point. Okay, excellent. This, of course, is a metric definition of open. You can define open in any topological space. Okay, great. So that's what it means to be open. And so here's how the proof goes. Okay, so here's the idea of the proof. Let P be a point in omega and find a circle CPR, okay, such that f of z minus f of p is not equal to 0 for all z in CPR. Now you might say, how can I do that? How can I make sure that this is possible, right? So here's the setup over here. So here's the complex plane. There's R, there's IR. Here's P over here, there's point P. And what I'm doing is I'm drawing a circle of radius R around P. And if this was impossible, to do this, then what could I do? Then I would say that there's a point on CPR where you're equal to f of p, right? So then that would say that you're over, maybe like over there, you were equal to f of p. Then in the next circle, by continuity, there'd be a point over here, 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 like that. I would be able to construct a smooth curve, right, going from this circle all the way to p, where f of z was equal to p, and that would say that f of z would be equal to p on a set with an accumulation point, and which contradicts the identity principle, right? So this is possible by the identity principle. This is possible. This follows from the fact that f is non-constant and the identity principle. When we prove the identity principle, you might have thought, my goodness, this is a very technical thing, points at topological thing, but we see over here the identity principle is going to give us the open mapping theorem, which is in some sense a strengthening of the maximum principle, right? Good. Okay, and the identity principle. Excellent. Okay. So now what we're going to do is, therefore, since it's not 0, hence there's a delta, there is delta greater than 0, such that the minimum over the set CPR of f of z minus f of p is bigger than 2 times this number delta over here, okay? And the 2 is artificial, but to make sure there's no fractions in my epsilon arguments, I'm going to put a 2 delta over there, okay? And that just follows, of course, the minimum. It's not 0, therefore the minimum modulus has to happen, right? It has to be some positive quantity, and whatever it is, it's bigger than some number 2 delta, because it's not 0, okay? Good. All right, and so now here's what we claim. So now what's going to happen is that your holomorphic function goes over here. It's going to map into the complex plane over here. There's R, there's IR. And you're going to go over here. That's where f of p resides, f of p. And what I'm going to do is I'm going to draw a disk of radius delta around f of p. Okay. And so now here's what I claim. So I claim that the disk at f of p of radius delta is contained where? Is contained in f of d p r. Like that. Okay? That's what we claim. And that's all we need to prove to show it's an open mapping. Because I said that f is taking this open set over here. This is an open set. F took the open set contains a what? Contains a disk, right? And of course, since open sets are in the complex plane are arbitrary unions of disks of this form, I can take unions on both sides of this equation and it works perfectly. Unions on this inclusion over here, and I get the result for free. Beautiful. So in other words, it's a local property. This is a local idea. And so if I can prove it for a disk, I get it for everything, okay? By taking unions. Excellent. That's what we claim. Okay. And so what we're going to do is we're going to let W be a point in df of p delta and consider g of z, which is f of z minus w, like that. Okay? Excellent. Now, how can I estimate g, right? So I can estimate g in the following way. So let's take a look at g of z is bigger than or equal to what? Is bigger than or equal to, well, let's not spoil the surprise. Let's just say what it's equal to. The modulus of g is equal to the modulus of f of z minus f of p. There was no f of p in there. I'm going to throw in another f of p minus w, like that. Okay. Excellent. And so now this, of course, is bigger than or equal to f of z minus f of p, and then minus f of p minus w by the triangle inequality, okay? And so now if we assume that z is where? I'm going to assume that z is on this circle, CPR, right? This is true. So this implies, hence, on CPR, what can we say? On CPR, for z on CPR, be more clear about this, right? It's not a hard idea. Let's say this. So for g, if z is on CPR, then what can we say? Then modulus g of z is on CPR, what you know about f of z minus f of p. It's bigger than 2 delta, right? So that's bigger than or equal to, strictly bigger than 2 delta, and then minus delta, because that's where w resides, right? So 2 delta minus delta. And so then you're going to be strictly bigger than what? You're going to be strictly bigger than this number over here. So you're strictly bigger than 2 delta minus this. So that's equal to delta. So g of z on the boundary, so in other words, the minimum of g of z on the boundary, so in other words, the minimum over CPR of g of z is at least delta. Okay? Good. But now what can I say about g of p? Well, g of p, what can we say about g, so I don't want to say that. But what else do we know? So what else can we say? So the minimum of that is bigger than delta, but in particular, we can say what now? We can say g at p, f of p, is what? So f of p, now where does w reside? So what's g of p? So g of p, for example, that's at the center of the circle. So g of p is the center of this circle. In other words, g, the minimum of g on this circle over here, is what? Is the minimum of g is bigger than delta. But what happens at p? G of p is equal to f of p minus w, right? So that implies that mod gp is equal to mod fp minus w, right? But what's fp minus w? So I know that fp minus w, well, w is in the disk of radius delta. So this is less than what? This is less than delta. So g of p, the minimum over here, the minimum over here of g over here is less than delta. That contradicts the minimum principle unless what? Unless there's a 0, right? So the minimum principle This implies by the minimum principle that G has a root. So G has a 0 somewhere in here. What does that say? G has a 0. Well, what does that mean? If G has a 0, that means that there's some Z in this disk over here. Hence what? Hence, G has a 0 over here. G of, let's say, Z tilde is equal to 0, which is that F of Z tilde is equal to W. Now, what does F of Z tilde equals W? F of Z tilde equals W means that you're where? You're over here in this disk. So that implies that W is where? Is in F of dP of R. W is in F of dPr. dPr. And that proves that this is an open mapping, so the claim is proved. This proves the claim. And that proves the open mapping theorem by my comment about unions, about open sets being arbitrary unions of such disks. Now, you might say, okay, well, big deal, it maps an open set to an open set. This gives us lots of information. If I tack on extra assumptions to this holomorphic function, namely if it's like injective or one-to-one, we're able to get a lot of information about the structure of the inverse function, right? So in some sense, what this will allow me to do is this will allow me to prove the inverse function is also holomorphic. So it gives me good results about existence of biholomorphisms and local inverses for holomorphic functions in regions where a function is injective, which we'll discuss in further videos. Thank you very much.